Hello there. So, I know we haven't been touching on the main expansion lately, but it's not changed ever since I last showed it in my video. So therefore, we don't need to show it again, and I don't feel like writing it because it's a very large expansion of 2 plus 2. But anyways, we're going to be creating the most complicated, most drawn out, extended, large, overly complicated, I already said that, formula for the area of a 4-dimensional sphere, or technically hypervolume. I don't know. I didn't technically hypervolume. So the last video, I just want to say that was just a proof of concept. We can get way worse. Anyways, let me show you real quick. Formula for a circle. Integral from 0 to r. Multiply that by 4. Seems like we're only doing about this much of it. Of the circle function. That is equal to pi r squared. There you go. That's very easy. It is a challenging integral. I've done it before. We don't really need to do it again, but I will just to show you again. But before we do that, we need to show the volume of a sphere. That is using something called the disk method, and it is 2, since it's technically like half the circle now, because what you do is you take the radius of a circle and you just create disks, and since like each disk is like this big, it'll be 2 instead of 4. So it's just in one little hemisphere. So you do 2 is the integral from 0 to r of pi r. Actually, no. Pi, and r is what changes, so that's what you use as a function. Whoops. The dx should not be in the square. And there you go. So this is actually a very simple formula to integrate because the square undoes the square root. So let's integrate that right now because it'll actually be really fast. Alright, so there's obviously the formula for this, which is obviously the formula for a sphere. Anyways, I just want to show that because it's actually very easy. We have 9 steps to it. Okay, so those are the easy ones. Now to get into our third formula. Formula, hypervolume for a hypersphere in 4 dimensions. Let's get started. So, you're still the 2, because you're still doing the disk method, except technically it'd be called the spherender method, because you're using spherenders instead of cylinders. Okay. 0 to r. There we go. There are our 3 formulas. Now, all you have to do is just plug in r. The r, like the r, the radius, not r, the radius, which is like this bit, the circle function, and we create an integral out of that. So we should have a triple integral that will be very, very hard to look at if you do not know where it came from, and it'd definitely be a challenge to integrate. So let's do that. So as first, obviously you're gonna start with this one because this is the lowest abstracted integral. Highest abstracted integral. 2. All right, and now we get into this part. This can be represented as an integral of this. So it'll be 2. All right, and the stuff in here can be represented as this integral. Alright, there we go. I thought it would be cooler, but I guess not. Does this mean that we have an integral formula in the means of a multiplicative series of an n-dimensional hypervolume of an n-dimensional hypersphere? That's precisely what I have. Looky here. That's a multiplication notation, just so you know. D is the number of dimensions that you want. And then, oh wait, hold on. I forgot the output that goes in here. That's supposed to be D. That dx is not in the multiplication sum. So there we go. That's the formula right there. You can see it. Let's see what it would look like for a 5-dimensional hypersphere. So it'll be oh, I just spotted a flaw. So let's look at the triplet integral for 4th-dimensional sphere. So this has to be D minus 1 because the 2-dimensional one, actually, this will actually only work if D is greater than or equal to 2, because you can't use this formula to find a 1-dimensional sphere, which is just 3 points on the line like this, where these two distances are the same. That's what a 1-dimensional sphere looks like. But that formula won't work because you can't really integrate that. And obviously this is the integral for a 2D sphere, so this will only work if D is greater than or equal to 2. There we go. Now with that bit cleared up, let's look at this. So this is a 5D sphere right here. This should be equal to pi squared r 4 over 2. That's the formula for a 4-dimensional sphere, the hypervolume. And you were just to simply integrate that. This means that we have, and we should technically, you can just move this to the back, or should we move this to back? So let's rewrite this as this. There we go. That's a bit better, because if you were to write it like this, you have nothing on this side of the integral. You'd have to move it to the other side. And this just makes it easier for you to visualize that. So this is the formula right here. Let me just circle it. Let's move this D is greater than or equal to 2 somewhere else. Okay, there you go. There is a formula, a series formula that is for the hypervolume of an n-dimensional sphere. Let me write that in terms of a 40 sphere real quick. There we go. There is a formula. We can use that. And then, like I said, we needed 100. So let's solve for R real quick with this formula. There we go. That means that this right here that is equal to 100. And thinking for that to our main expression because it seems that 100 is one of the few numbers that we did not touch that in 1500. Yeah, so hope you enjoyed this little portion right here. Alright, so this portion is for the most of my viewers who probably do not understand because as it is famously obvious in all my other videos, I'm very poor at explaining things. So let me show you this little bit and hopefully you'll understand.
Light work, no reaction. Light work, no reaction. Light work, no reaction.
Light work, no reaction.
Okay, it's got a little kick. Oh, it's got a little. Okay.